Hello everyone, this is Xiaolan, a second-year PhD student from University of Arizona. Today I'm going to present a privacy predetermined technique for key-value data collection. This is a joint work with my advisor, Professor Ming from University of Arizona, Dr. Yueqiang Cheng from Baidu Security, Professor Xiong from Emory University, and Professor Yang Cao from Kyoto University. The main work was done when I was a summer intern at Baidu. I will first give you some background of local differential privacy, introduce the problem statement and the existing mechanism. Then I will focus more on our framework called PCKV. Finally, I will show some experimental results and conclude our work. Recent years, many companies are collecting our private data to provide better services. However, there are many news on privacy leakage which raises our privacy concerns. A possible solution is a data collection model with local privacy guarantees. In this model, each user will locally perturb her raw data by a randomized mechanism, then upload the perturbed data to the server. Finally, after collecting all users' data, the server can implement some statistical analysis for better services. Here, the server is often assumed to be honest but curious. In this work, we focus on the privacy solution called local differential privacy. We call a mechanism M satisfy epsilon LDP if and only if for any pair of inputs X and X prime and any output Y, the probability ratio of outputting the same Y is bounded by the exponential of epsilon. X and X prime are the possible inputs. Y is the output. Epsilon is the privacy budget. Here, a smaller epsilon indicates stronger privacy because an adversary cannot infer whether the input is X or X prime with high confidence. LDP has been widely adopted by many companies, such as Google and Apple. A very basic LDP protocol is randomized response. It reports the truth with some probability and only works for binary answer. Specifically, each user has a truth X, which can be 1 or 0. They randomly flip the bit with probability 1 minus p. The perturbation probability p depends on epsilon to satisfy epsilon LDP. After aggregating all responses, the server can estimate the frequency by some estimator with unbiased property. There are some extended versions of randomized response to work for domain size with more than 2. The first one is optimized Unary encoding. It first encodes the input into a bit vector and then independently perturbs each bit. Another one is generalized randomized response. It directly perturbs the input with some probabilities. These are building block mechanisms for frequency aggregation and will be used in our problem, private key-value data collection. Let's consider a movie rating system. The movie is a key and the rating is a value. Assume each user has different number of key-value pairs because some people rate only one movie and some people may rate hundreds of movies. The key is indexed by 1 to D. The value is in the range of -1 to +1. In this work, we focus on frequency estimation and mean estimation. The server is assumed as honest but curious. Our objective is to design a good mechanism which has better privacy utility trade-off. This problem has several challenges. The first one is each user has different number of key-value pairs, because reporting all pairs will lead to a small budget and large error in each pair. The second one is if a fake K is reported, how to report the corresponding value, and how to design an optimal maximum with the best privacy utility trade-off. An existing maximum is private KVM. It converts the key value pairs into a vector and iteratively updates the mean of each K. In each round, each user will randomly sample an index from 1 to D and then privately report one pair. There are some limitations of this maximum. First, the multiple rounds require all users to be always online, and the privacy budget in each round is very small. The naive sampling protocol may not work well for a large domain, and there is no improved privacy budget compensation. On the other hand, our mechanism has only one round. It uses the advanced sampling protocol and has tight privacy budget compensation. Now let's move on our mechanism. Our framework includes two maxims. PCKV-UE is based on Unary Encoding, and PCKV-GRR is based on Generalized Randomized Response. In both maxims, each user will first pad her case into a uniform length L by some dummy case, then sample one key value pair. It can improve the sampling efficiency because L is much smaller than domain size D. Then, due to the joint perturbation and joint privacy analysis, the privacy budget compensation is tighter and the privacy utility trade-off can be improved. After collecting all users' data, the server can implement the aggregation and estimation, where we theoretically evaluate the utility by MSE of estimation. Since the estimation error can be theoretically analyzed, we can minimize the error to get the optimized design. Let's look at some details. In the joint perturbation, we first do the value discretization and randomly perturb the K with privacy budget epsilon1. If a fake K is reported, we will report the value with the same probability, 0.5, to cancel out the contribution of fake values. Since this step totally lost the information of value, it also results in mass privacy leakage, which is the intuition of our advanced privacy analysis. If this is not a fake K, we will randomly perturb the value with privacy budget epsilon2. When jointly analyze the privacy of PCKV-UE, we will find the final privacy budget is less than epsilon1 plus epsilon2. We call it tight privacy budget compensation. PCKV-GRR has similar tight compensation and additional privacy benefits from sampling. However, private KVM does not have tight compensation. After collecting all users' data, the server will compute the supporting number of two different values and implement the estimation. We show that the frequency estimator is unbiased and the mean estimator is asymptotically unbiased. We also explicitly represent the theoretical mean squared error as a function of epsilon1 and epsilon2, which makes it possible to minimize the error with the optimal solution. With the tight privacy budget composition, we minimize the MSE of estimation, then obtain the optimized privacy budget allocation, which gives the optimal epsilon1 and epsilon2 when the total privacy budget epsilon is given. And finally, we can obtain the optimized perturbation probabilities of the two maxims. In summary, PCKV first choose the advanced sampling protocol, then jointly perturb key value and jointly analyze the privacy. Finally, it optimally puts all things together. We use synthetic data to validate the performance of frequency estimation and mean estimation. Smaller epsilon means more private. Smaller MSE means more accurate. We can observe that private KVM has larger MSE. Our maximum has smallest MSE on both frequency estimation and mean estimation. Also, the theoretical results shown by dashed lines close to the empirical results shown by solid lines. Consider our framework has multiple improvements. We separately show the benefit from each improvement, including the tight budget composition and optimized budget allocation. For the top frequency K identification, where the higher precision means more accurate, we can observe that our maximum has the best accuracy, and PCKV-UE only gets small impact from large domain size. We also implement this maximum on real-world datasets with more than 10,000 of domain size, where our maximum is the best. In summary, besides an advanced sampling protocol, our framework considers joint perturbations to provide more options for maximum design and the chance to choose the optimized one. It also results in tight privacy budget composition by joint privacy analysis. Our future work will focus on the optimal L, impeding and sampling protocol, and the general tight composition analysis of other types of data. Okay, that's all. Thanks for your listening.